In this video, we're going to talk about factoring polynomials. Now, essentially where we're going with this is kind of doing the reverse of what we learned when we're talking about multiplying polynomials. Factoring would be just kind of undoing that multiplication process. But before we get too far into it here, let's just start with some basics. So first of all, when I say the word factor, we want to think about multiplication. So just kind of as a beginning example here, up at the very top, we would say that 3 and 4 are factors of 12, right? Because 3 times 4 makes 12, right? Or another way of putting it is 3 and 4 are factors of 12 because 3 divides into 12 evenly, and 4 also would divide into 12 evenly. All right, so if you are looking at a number, first of all, and wondering what factors it has, a lot of times it's nice to give the prime factorization or write a number as the product of prime numbers. If we do that, then it makes it a lot easier for us to tell what the greatest common factor would be of a list of numbers. Okay, so let's do some examples of this down here. So if I ask you what's the greatest common factor of 45 and 75, what I'm asking you to do is tell me what is the very largest number that could divide evenly into 45 and divide evenly into 75. Now, on the one hand, you may be able to just look at these two numbers, and you've had enough experience with numbers to know that the greatest common factor is 15. Because 45 divided by 15 is equal to 3. It goes into 45 evenly. And 75 divided by 15 is equal to 5. And there's nothing larger than 15 that would divide into both of these numbers evenly. Okay, so you might just know that, but let's say you didn't. Then what you could do is what we call prime factor both of these numbers. So the way you prime factor is you just look at 45 and you say, what are two things that come to mind that multiply to make 45? All right, well, 5 and 9, right? 5 times 9 is 45. Now, when you hit a prime number, right, the prime number is just a number that can only be divided by 1 in itself, then you stop. But if the number is not prime, if it can be broken down further, you go ahead and do that. So 9 is 3 times 3. And of course, 3 is a prime number, so we'd stop there. So what we have here is that 45 is equal to 5 times 3 times 3. And you can punch that in your calculator, you of course get 45. Then we do the same thing for 75. All right, so 75, maybe the first thing that comes to mind is 3 times 25, right? 3/4 is 75 cents. 3 is a prime. And of course, 25 is 5 times 5. So when we're looking for the greatest common factor, what we have to do is we say, okay, well, what do they share in common? Well, they share a 3 in common, right? And they share a 5 in common. But they don't share any more than that, right? This one has another 3, but this one doesn't have a 3 to pair up with it. This has a 5, but no 5 to pair up with it here. And so to find this greatest common factor by prime factoring, you would just take the product of the primes that are shared by both. And that's how you could get 15. So when we take something like 8 and 33, you might look at that and say, boy, I can't really think of anything that'll divide into 8 and divide into 33 evenly, other than 1. So you can confirm that by prime factoring. So 8 prime factors into 2 times 2 times 2. 33, well, that's 3 times 11. So see how they share no prime common factors? So we would say then, since 1 goes into everything, our greatest common factor is 1. All right, 8, 24, and 60, you know, maybe try this both ways. Try just kind of thinking about it, thinking about what do you think the biggest thing that goes into all of them is, and then try the prime factorization. So 8 is 4 times 2, 2 times 2. All right, 24 is 4 times 6, which breaks down. And then 60, 6 times 10, 2 times 3, and 2 times 5. And so what I'm looking for here is what do they all share? All three of them have to share it. So if I circle this 2, I can circle that 2 and that 2. So they all share at least one common factor of 2. Well, let's see. Looks like another 2 will do. Right? They all have another factor of 2. Sorry, I don't know what this is. So times 2. And then I'm just looking for other stuff. So we got a 3 in both of these, but no 3 in 8. So that's out. Another 2 here, and another 2 here, but not another 2 in 60. And 5 only shows up in 60. So this must be it. The greatest common factor is 4. So in other words, I can divide 8 by 4, I can divide 24 by 4, I can divide 60 by 4 evenly, but nothing larger can I do that with. So that's the greatest common factor of a set of numbers. Okay, now we can do the same thing with variables. Okay. So when we're looking at variables, the greatest common factor is the same idea. Okay, what could I divide all of them evenly by? Which is a little bit less intuitive maybe than when we're talking about that with numbers. So maybe think of it this way. We have y to the 4th, y to the 5th, y to the 8th. So a y to the 4th, if I divided y to the 4th by itself, I'd get 1. If I divided y to the 5th divided by y to the 4th, I'd get y. Y to the 8th divided by y to the 4th, I would get y to the 4th. So basically the smallest power of y ends up being our greatest common factor. So for x and x to the 10th, it would just be x, right? You can divide x by itself to get 1, and x to the 10th by x to get x to the 9th. And so using this lowest power idea, we just do the same thing here. We have an x squared, and an x. Right? So we can have an x in our greatest common factor, y cubed, y squared, y to the 4th. Well, we got to take the smallest one, y squared. All right. And then, of course, we can combine these. We can look at numbers and variables. So you just want to take it one at a time if I'm asking for the greatest common factor of these. So, I look at 9, 15, and 6. Right? What's the biggest number that I can divide 9 by, 15 by, and 6 by? Well, it would be 3. Right? That's the biggest thing that would go into all three of those numbers. X squared, x to the 4th, and x to the 1st. Well, the lowest power is x, so 3x is my greatest common factor. Now here we have 11, 1, and 1. Okay, so numerically, I'm just going to go ahead and write it, even though we usually don't. It's just 1. A squared, and a, just one factor of a. B cubed, b squared, so that means the lowest power is b squared, so ab squared. All right, and this would be a good time to pause, try part C on your own, see if you got the hang of this. All right, so I'm looking at 12, 30, and 42. Okay, so let's say that it's not clear to us, so we had prime factor, right? So I'm going to go 4 times 3, 2 times 2. By the way, when you do this, it doesn't matter how you started. If I had gone 6 times 2, I would end up with the same prime factorization in the end. So it doesn't matter how you get the prime factorization started. 5 times 6, 2 times 3. 7 times 6, 2 times 3. And I'm just identifying what do they all share. They all share a 2, and they all share a 3. So that means 6 is the numerical GCF of all those, and then the lowest power is y squared. All right, so far we've just found the greatest common factor of a list of terms. Okay, but what are we really trying to do with this? I said at the beginning that really the purpose of this is to kind of undo that process of multiplication that we did before. And so first I want to think about the distributive property that we used, right? So if I have something like 5 times 3x plus 2, we know that that distributes through and becomes 15x plus 10. And so when I say I want us to factor something, factoring means go back the other direction, right? So in other words, to go from this to this in that direction, that is me multiplying or distributing. To go from here to here is to factor. So if I take something like 49x minus 35, I want to factor out the greatest common factor. Well, 49 can be divided by 7, 35 can be divided by 7, so if I pull a 7 outside, then in this term I think to myself, what do I multiply 7 by to create 49x? I would multiply it by 7x. What do I multiply 7 by to create negative 35? Multiply it by minus 5. Part B here, no numbers to speak of, but remember that when we have a set of variables, we pick the lowest power. So I should be able to pull an x outside. And so I ask myself, x times what makes x to the 4th? It would be x cubed. X times what gives me negative x? Minus 1. All right, one more here. Negative 12, 10, and negative 2. Well, I can pull a 2 out of there. And, you know, it kind of depends on the instructions on a homework problem, but what I would say is it's always nice to have the highest degree term, meaning the one with the highest power. It's always nice when that's positive. So not only am I going to take out a 2, I'm going to go ahead and take out a negative 2. And then ask myself, oops, almost forgot. That's just the numerical part. And then for the variable, we have a b to the first, so take out negative 2b. So I ask myself, what do I multiply negative 2b by to make negative 12b to the 5th? Well, negative 2 times 6 makes negative 12. And b to the 4th times b makes b to the 5th. Really trying to make that look different than my 6. I kind of regret my letter choice there. But definitely a 6 here and a b to the 4th here. All right, what do I multiply negative 2 by to make positive 10? I'd have to multiply that by negative 5, right? B times what makes b squared? B times b makes b squared. And then negative 2b times positive 1 makes negative 2b. All right, so this is me factoring out the greatest common factor. Okay. Now, if we move down here, in the multiplying of polynomials section, one of the things we did learn was how to multiply two binomials. And it turned into something like this. So that really did rely on the distributive property. And remember that FOILing was just kind of a shortcut to that process of distributing. So in the same way that I should be able to, if I know how to distribute something like this, I should be able to factor it and get back to where I started. If I see something like x squared plus 7x plus 12, maybe I can go back this way to where I started, right? So even though I look at x squared, 7x, and 12, and I see there's no common factor, what we're going to try to do is go from there to there, and we're going to call that factoring as well. All right, so what we want to do to factor something like this is we want to remember how you multiply it out. In other words, let's take x squared, 7x, and 12, and let's remember where these different parts came from. So remember that x squared came from the first times the first. 12 came from the last times the last. And then the 7x, remember that came from outside plus inside. Okay? And I'm sorry, this looks like I'm doing example 5. We'll do example 5 in a second. Let's, I'm doing the one from the example itself above. So here, we'll do that in a moment. But here's what I want to do. I want to say, if x squared had to come from the first times the first, then I really have no choice but to do this. X times x is x squared. Now the 12 has to come from this times this, right? The last times the last. But the tricky part is, the last times the last, there's different ways to make 12, right? There's 1 and 12, there's 2 and 6, there's 3 and 4. But the way we make our decision is we look at the middle term and we say, okay, well, outside plus inside, that's got to be my, that's got to make 7x. So you look at these and you say, which one of these makes 7x? Well, there's our winner, right? And we can see it there, right? But since 3 plus 4 is equal to 7, then I can confidently say, oh, okay, it must be 3 and 4. And it's always good to double check your work on these types of things. You can say, all right, well, there's my inside, and there's my outside. If I add them, do I get 7x? Yes, I got the same thing that I started with. And so that is our answer. So sorry. So now let's actually do example 5. We'll do that in red here. Sorry if you don't have quite as much room on your paper. So x squared plus 5x plus 6. So I say to myself, I know I want x and x, because first times first needs to make x squared. I know that last times last has got to make 6, so I have to think about what are the ways to make 6. 1 and 6 and 2 and 3. But clearly 2 and 3 are going to add up to 5x, so that means plus 2 plus 3, and that's got to be my answer. Now it's important to note here, not all trinomials like this, trinomial meaning 3 terms, not all of them can be factored. There'll be plenty of times where it just won't be possible, right? So that's okay too. But if they can factor, this is how you're going to find it. So if I were to, and I'm really kind of just doing extra questions here, but let me just write over here real quick. If I did x squared plus 5x plus 7, and I tried that process, I could still put x and x here, but then I'd look at 7 and I would say, all right, how do I multiply to make 7? It would have to be 1 times 7, right? But can 1 plus 7 make 5? No. And so this one can't be factored. Okay. All right, so we're going to kind of run through a few of these. And obviously this is something you've most likely done in the past. If you haven't, definitely let me know, and so we can kind of work on some of this together. But this might be good, especially if you have some experience. Just pause and try to do the next 4 examples. But I will kind of walk us through all 4, because these next 4 really kind of show the different scenarios that do pop up. All right, so this first scenario is where both the middle term and the last term are positive. When that happens, and you think about your last, you do what we did on the previous problems. You list out the different ways to multiply to make that number. and you see, do any of them add up to make the middle term? And you can see here, 4 plus 5 equals 9. And so that means we can confidently say it's 4 and 5. Okay, so that's just like the examples on the previous page. Okay, but in a different scenario we haven't seen yet is what happens when the middle term is negative and the last is positive. So I'd go and say, all right, I want x times x. Now, the last times the last has to make positive 22. Okay, last times the last has to make positive 22. But here's the thing, there's two ways to make positive 22. You could multiply a positive times a positive, or you can multiply a negative times a negative. So seeing this middle term as negative tells me, you know what, when I'm listing these out, I should be listing out negative 1 and negative 22 so that they can add together to make a negative middle term. That doesn't work though, so let's try negative 2 times negative 11. Ah, that'll do it, right? Negative 2 plus negative 11 does equal negative 13, like I have here. So then I know it should be minus 2 minus 11. Okay, what about if the middle term is positive, but the last is negative? Well, here's where things get a little trickier, because we have x, and then negative 36, I need this to multiply to make the last time the last multiply to make negative 36. So when we want to make negative 36, the signs on the numbers we're multiplying have to be opposites, right? Negative times positive, positive times negative. So I need to think about negative 1 and positive 36, negative 2 and positive 18. Negative 3 and positive 12, negative 4 and positive 9. All right, and then negative 6 and positive 6. And what you'll find, okay, so I think I got all the multiples here, or all the factors here, but then I really should be flip-flopping, right, which one the negative goes with as well. Now in practice, what you're going to probably do is not list all these out like I am. You're probably just going to list them out here, right, these first 5, and then just know, okay, but I can put the negative on either one I want. But out of this entire list, one of them does add to make positive 5, right? And that would be this one. Negative 4 plus 9 is equal to 5. So I know that is my factorization. And again, don't lose track of the fact that how do you know you did it right? Right? If you FOIL it back out again, right? First, outside, inside, last, right? If you FOIL it back out again, x times x is x squared, x times 9 is 9x, negative 4 times x minus 4x minus 36 does give me that same thing back, right? So don't lose sight of that. That's ultimately where all this is coming from. All right, and then example 9. Now we've got a negative in the middle and a negative in the last, so we're looking for q and negative 40. Negative 40 is what we're trying to make. So 1 and 40, so negative 1 and 40, negative 2 and 20, negative 4 and 10, negative 5 and 8. And again, probably would just stop there, but this is to be, extra careful about it. This is all the possibilities right here. And so we're looking for something that adds up to negative 3. So I see that 5 and 8 are a difference of 3, so 5 plus negative 8 gives me the negative 3 I'm looking for, so plus 5. minus 8. All right, so those on that page are really the 4 different scenarios, right, based upon where pluses and minuses might be. Now on this last page, the point of this last page is I want you to never forget the easy type of factoring, right? So we just worked hard to remind ourselves how to do this reverse FOIL process, is kind of like what I call it. But don't forget about this stuff right here, right? From example 4. If there's something common to every term, pull it out of every term. So here, you might look at this and say, okay, this looks different than the last page. Well, yes, it does. However, we should recognize that I can pull an x out of all 3 terms, and that would leave me with x squared plus 3x minus 4. And then the thing that I'm left with in there, maybe I can do that reverse FOIL process to it. So I'm going to see, can I do this? And of course, negative 4, well, that could be negative 1 and 4. It could be negative 2 and 2, or it could be 1 and negative 4. And we can see that that very first one adds up to be our middle term. So I can say minus 1 plus 4. So don't forget easy factoring, factoring something out of every term. And clearly that's what's going on here in example 11 as well. So I can see that there's a factor of 5 common to every term, so I can pull that out. And then my smallest power is x cubed, so I can pull that out also. So 5x cubed times x squared would give me 5x to the 5th. 5x cubed times minus 5x would give me negative 25 x to the 4th. And 5x cubed times negative 6 would give me the negative 30x cubed. And this again looks a lot like what we were doing on the last page, so let's give it a shot here. Alright, so we're making a negative 6. We've got a negative 1 and a 6, negative 2 and a 3, 2 and negative 3, and a 1 and a negative 6. So looks like this one adds up to be negative 5. So we'll say plus 1 minus 6. And then this last example here, example 12, first of all, a couple of things that might look weird about this. First, you look at the previous page. All these ones we did, the square term came first, and the square term was positive. So in this one, it's easy enough to make the square term come first. You can always reorder addition. It's no problem. Right? That's not a problem. But there's a negative in front. So we really would like to have, it's not a 100% a necessity, but it's nice if the x squared term is positive. So you can always make that happen if you pull a negative out, just pull a negative 1 out of every term. So negative 1 times positive x squared gives me negative x squared. Negative 1 times negative 12x gives me positive 12x. Negative 1 times positive 11 makes negative 11. And then I can factor this if possible. So 11 is going to be 1 and 11. That's the only hope. But look at that. Negative 1 times negative 11 will do the job because adding those together makes negative 12. So I can say that this is my factorization. Now we're not done with factoring. There's another video right after this that will cover even more complicated forms of factoring. This is just one of those topics where I I'm sure you've all done it before, but this is one of those where I think you'll be grateful for the review. And again, if you're struggling at all with this, let's get together and talk through some of them, and help let me work with you on these, because this is a skill that we're going to be using pretty consistently throughout the course.